All right, we were in section 11.1 last time, and we were looking at some common notions or basic notions of geometry, and we're going to continue that both from 11.1 and definitely into 11.2 as well. A lot of terms, a lot of terminology, just to make sure that everybody is remembering the details the same way. So let's take a look at these questions first, and we'll kind of get back into some of what we were talking about last time with parallel, skew, planes, things like this. So the first question says, if 2 points are in a plane, then the line containing them is where? So what do you think? Where would the line containing them be? In that plane, exactly. Okay, so if there's 2 points in the plane, then the line that contains them is also in the plane. All right, so now let's say that we have a line, and we have a point not on that line. What kind of an object or image will that determine? A line and a point not on the line. Any ideas about what that might be?
Coplanar?
Yeah, they will be coplanar, which means they determine a plane. Right, very good. So this actually determines a plane. If you imagined a line segment, it might be a little bit easier. If you had a line segment, like so, that's not very good, but pretend for a moment, and you have a point not on it, this actually would determine a triangle, right? Okay, which is a planar surface, right? It's a two-dimensional object. That two-dimensional object lives inside of a plane. Okay, because we don't really have a line segment, we have a line, which means it continues on in both directions, forever, right? All right, the third one, 2 different parallel lines determine what? Yeah, they are coplanar, so again, they determine a plane. Are you sensing a pattern on this slide? So what if you have 2 intersecting lines? Yes, they determine a plane. And we talked a little bit about this image last time, so let's go back and look at these last 2 images anyway, because I kind of rushed through them. The third one says 2 parallel lines, so you can imagine having the parallel line of the top over here, the line with the ceiling and the wall, and then with the floor and the wall, right? They're parallel lines. What do they determine if you can take them all sort of as a whole? Well, they determine the plane that is the wall, okay? So you can do the same thing with intersecting lines. So if we take the line that's along the top again, and we take the line that maybe is along the top of the room behind me, right, that meets the ceiling with the wall, those determine a plane. Which plane? What plane would contain both of those lines? The ceiling, right, the plane that is our ceiling. All right, so that would determine a plane as well. All right, now we're going to talk a little bit more about lines and planes, how they relate. If we have 2 planes now, okay, so we were talking about lines and points a minute ago, but now we're going to have 2 planes. So we have, the wall and the ceiling, the wall and the floor and the ceiling, and so forth. 2 planes. We could have planes that are parallel. So give me an example in this room of 2 planes that are parallel.
The front wall and the back wall.
Floor and the ceiling. What do you have?
The front wall and the back.
The front wall and the back wall, or the 2 side walls, right? So those would be parallel planes. They are planes that have no points in common. The next one is intersecting planes. So if we have the intersection of 2 planes, they will intersect in a line. So can you give me 2 planes in this room that intersect? What do you think, Jacqueline?
That wall and the ceiling.
Okay, so the wall over here by the door and the ceiling, they intersect in what line? The one that's on the top, right? This top line right here along the ceiling and the wall. Okay, so we have lots of them. We could use any of our walls and ceilings, or even the floor, right? And then we'd do that in this room, right? Okay, great. We could also use 2 walls in this room to do that, right? So if we used the wall with the door on it, we use the wall with the chalkboard on it, those would intersect, and they'd intersect in this line right here that's in the corner, okay? All right, some more about lines and planes. Now we're going to talk about the relationship of lines to planes. If we have a line and a plane, so not 2 planes, but a line and a plane, we have 3 ways that that line and the plane can interact with one another. One option is it could be parallel. They have no points in common. Okay, so can you picture in this room, pick a plane in this room. Everybody pick the same plane. Somebody tell me a plane you want to pick. The ceiling. Okay, Give me an example of a line that would not intersect my ceiling. The one behind me along the floor, right? That line does not intersect the ceiling, so we would say that line is parallel with the ceiling. What's another line that would be parallel with the ceiling? Yeah, the wall over here where it intersects the floor. In fact, everything along the floor, these are the images that are easiest for us to sort of think about in the room we're in, right, would work, right? They would all be parallel to the ceiling, okay? So that's one option. The second option is that it's intersecting and it's contained inside of that same plane. So let's stick with our ceiling. What lines in this room would intersect our ceiling and it would be contained inside of the ceiling?
Corners.
Those are points. We want a whole line.
Ceiling tiles.
Okay, so these would be good examples. So all of these they look like these lines along our ceiling actually as well. You can also do this sort of edges that we've been looking at. Those would be okay too. So all of these edges, all of these lines themselves that you're seeing along the ceiling tiles, they look like silver lines on my ceiling, right? Those would all be lines that are inside of the plane that is our ceiling. Okay? Last option. It could be intersecting but not contained in that plane. So again, let's make the plane our ceiling. Where would we have, that's right, so Skylar's telling me if I have this line right here that connects my two walls over here, that one intersects the ceiling, right? But it is not contained inside of the ceiling. So that's a good example. Okay, so these are three ways that a line and a plane can be related to one another. Perpendicular lines and planes. If we have perpendicular lines, these are lines that form right angles when they intersect. Okay? You've seen them before. If we draw them in 2 dimensions, they look like this, right? These are perpendicular lines. Do you remember the notation, like in the image of the picture, of what they do when they tell you, like when a book tells you this is perpendicular, how does it draw it? Yeah, a little right angle right here, yeah? That's how you know for sure that they really mean that they're perpendicular, not just maybe it looks sort of like it, okay? Now, in terms of notation, let's give these lines some names. Let's call them L. Does it have names here? J and K. Sorry about that. So we'll call them J and K. Do you remember how to write that they are perpendicular, the notation? Yeah, it looks like that, right? Mm-hmm. And the order doesn't matter, so we could write J perpendicular to K, or we could write K perpendicular to J. That's the notation for it. You can also have a line that's perpendicular to a plane. That will happen anytime you have it perpendicular to every line in the plane that it intersects, right? So if we imagine, again, our ceiling, and we imagine one of these corners where it meets the wall, the two walls meet, that'd be perpendicular to the ceiling. Because it would be perpendicular. You can imagine the line in the plane up here, right here. It'd be perpendicular right up there in that corner, right? And if you imagine the line that's right here that it goes through along the ceiling up here, it would also be perpendicular up here in the corner. And again, we don't see it as well, but there would be a line sort of coming out of this, going straight back to the other corner of the wall. It would be perpendicular to that one as well. It'd be perpendicular to all of the different lines that are in the plane in order for it to be perpendicular to the plane. And then if we have two planes that are perpendicular, then any angle that is formed by a line in one plane and a line in the other plane is a right angle. Can you see two perpendicular planes in the room? The wall and the ceiling, right? Any of the walls in the ceiling, any of the walls in the floor are perpendicular. They are creating a right angle where they meet with one another, right? All of the lines. So if you imagine the line that comes down along this pillar right here, along this wall, and this line that goes along the floor like this, they're perpendicular, right? And you could do that with any of the lines like that that they intersect in. All right, we're going to move a little bit away from planes and lines and such, and we're going to move into angles. Angles relates another topic that we encountered last time. An angle is formed when we have two rays. Okay, so a ray, remember, is your book also sometimes calls it a half line, is a segment that continues on one end. Whoops, try that again. And it has an end point of the other. So this is a ray. If we have two rays and the end points are the same, that creates an angle. So here's one ray, here is a second ray, they have the same endpoint. When that happens, we create something called an angle, and it's this measurement right here. The rays themselves are called the sides of the angle, and the shared endpoint is called the vertex. So in my picture right here, this is the vertex, and this is a side. The interior of the angle is a part of the plane that is between the two sides of the angle. So this picture right here is the same one I was drawing above. So you can see it's shaded in very nicely right in here, the interior. In fact, let me just point to it. Right in here, this shaded part is the interior. And of course, it extends, right? It continues on forever towards the right, as long as it's contained inside of those arrows, those rays that are going towards the right-hand side as well. We label an angle in multiple ways. Is that on the slide or is the next one? I think it's on the next one. Angles are named in multiple ways. One way they can be named is by a Greek letter. Alpha, beta, gamma, whatever. Okay, so you might see a Greek letter labeled here. There's alpha and a beta on here. Or they might be labeled by a number in there. You could see a number written in there where those Greek letters are. Sometimes that happens. Very specifically, if you use 3 of the points, one of them being the angle's vertex, and then the other 2 being on either of the 2 sides, you can label the angles that way as well. So let's actually take this top angle, this one right here, that's called alpha. So the angle that is alpha is also, hang on, let me write this correctly. Angle alpha is also angle what? How else could we write this angle to identify which angle we're talking about with the letters? All right, so this is angle Q, P, R. Is there another way to write that angle? Well, not PRQ, but you're close. RPQ, yeah. We need to make sure that the vertex is in the middle. So if you imagine starting along one of the edges and going around the angle, that's how we're going to write the angle measure, sort of in order like that. Okay? And we could do the same thing with beta. I'm not going to, but it's the same process. We could go and we could do the same thing with beta. We talk about 2 angles being adjacent if they share a common side. So this one has side what in common? PR. It's the one that's on, it's a part of both angles, side PR. But they do not share part of their interior, right? There's no overlap of that shaded picture over here. The shaded parts on the inside of each of them, they don't overlap. So we don't have like this piece overlapping with this piece, right? There are ways that we could draw angles where the interiors do overlap, and they do share sides, but because they shared interiors, it wouldn't define, this definition still wouldn't work. Okay, so they don't overlap in any fashion. All right, the most common way of measuring angles, and the one that we're going to use in this class, is called degrees. Everybody remember working with degrees? Okay, good. Do you remember how many degrees are in a circle? 360, fantastic, good memory. So if there are 360 degrees in a circle, then 1 degree is how much of a full circle? How much is 1 degree of your whole circle? One over 360. I know some of you are scared of fractions. They're not scary, I promise. It's 1 over 360. It's like saying how much is a penny of a dollar? Well, it's 1 over 100 of a dollar, right? Yeah, same thing. It's 1/360th of a full rotation or of a circle. We can break degrees down as well. You might think, but the degree is so small, why does it matter? Well, there are situations where we would want to be even more precise than degrees would be. We can break them down into minutes, and we can break them down further even from minutes into seconds, which starts to feel like we're working with a clock. And we have that 60-degree thing going on, right? And how many minutes do you suppose are in a degree? 60. And then thinking about your clock, how many seconds are in a minute? 60. So we're all working with the same thing that it looks an awful lot like our clock, which is a circular object that we use all the time. So our goal in the next few slides is going to be able to be working between minutes and seconds and degrees. Okay, so we're going to be working and converting between those things. All right, so this slide, what we're going to do is we're going to take something that is given completely in degrees. It's 32.46, or 32 and 46 hundredths of a degree. And we're going to take that 46 hundredths in particular, that 0.46, and we're going to figure out how many minutes, how many seconds that would be. Okay? So as we're working through these, this is going to feel like something some of you have done before in number theory or elementary math 1 if you've taken that course. It's going to feel like conversion of bases, because it is. It's exactly what it is. Okay? So the first thing I'd like for you to do is what we did in that particular class. We're going to write our degrees here, and we're going to have minutes and seconds when we're done. Okay, so this is our goal. We know how many degrees we have. That's already given to us. How many degrees are in this measurement? 32. So I don't have to do anything to get that. It's the 0.46 that I have to convert. All right, so how do I do that? Well, if I take my 0.46, what I'm going to do is I'm going to multiply by 60. Because I'm taking a portion of a degree and I'm multiplying it by there are 60 minutes in a degree. Okay? So someday if you have a calculator with you, or I don't want you to do it by hand, but grab a calculator if you have it, multiply 60 times the 0.46. And what this is going to give me is this is going to give me the number of minutes. Okay? I multiplied by 60 because there are 60 minutes in a degree, and this will tell me how many minutes I have when I'm done. And I am fully aware that you're going to get a decimal, and that's okay. Okay? We'll figure that out in a sec. What'd you get?
I got 27.6.
Okay, 27.6 minutes. And the minute mark looks kind of like a hash mark or an apostrophe or something like that. Okay? So this is 27.6 minutes. So how many whole minutes is it? 27. So I've got the answer partially now for my, I'm filling it as I go. I've got 32 degrees, now, and 27 minutes. But I've got this portion of a minute. How do you think I'm going to turn that portion of a minute, that 0.6 of a minute, into seconds? I'm going to multiply by 60 again. So I've got 0.6 this time, and I'm going to multiply that by 60. This will give me my number of seconds. So what is 0.6 times 60? This is 36 seconds, and seconds is this double hash mark, looks like double apostrophe. So my answer to the question is 32 degrees, 27 minutes, and 36 seconds. And that's how you write it. It's okay? So jot yourself a note on this slide that says something like, degrees turning into the degrees, minutes, seconds is a multiplying feature. It's all about multiplying by what number? 60. Because actually 60 is the base of this number system. Numeration systems. Some of you have seen it before, some of you haven't, but it's the base of this number system. Okay, now we're going to go the other direction. We're going to go from degrees, minutes, seconds into just degrees. So if I multiplied to go the other way, what would I do on this one, do you suppose? I'm going to divide. So write yourself a note that this is division. We are going to divide. What are we going to divide by? Well, we're going to divide by the base. So it's 48. I don't have to do anything with that. I'm going to put a plus sign because I really am adding these together. The 57 is in minutes. So I would write 57 over 60. That's the division that I need because there are 57 minutes out of 60 minutes total in a degree. What do you suppose I'm going to write the 36 over? Close. It's not 120. 3,600. How did you get 3,600?
Well, you have to divide by, or you multiply by 60 twice, so.
Yeah, we multiplied by 60 twice to get the seconds, so we're going to divide by 60 twice to get the seconds back into degrees. You can also think about in terms of your clock. If you want to figure out how many seconds are in a minute, you multiply by 60. But if you wanted to do that for hours, you'd multiply by 60 and then by the 24, right? So it's the same thing. You multiply by the base ahead. So this, in some sense, I realize I could write it the same way that Kaylee told me to, but I'm going to write it as 60 squared just to remind ourselves where the 3600 came from. So again, your calculator can do all of that for you. I want to see some notation of what you're doing, right? So this is a pretty good, reasonable, small amount of work to show. This will work, that you're dividing one by 60, the other one by 60 squared. And then I need an answer, and it will be in decimal form, 48 point something. What'd you get?
I added them all together at
Mhm.
the time. And
Yep.
for the total answer, I got 49.31.
Can't get anything over 49. So there's probably an error in what was doing the division. Did you get 9.6? Okay. Yeah, so check that one again and make sure. All right, so 48.96. Everyone who had a calculator, did it give you that? Is it okay? Okay, great. This is the correct value. Did it work that time?
Yeah.
Okay, good.
I had squared the whole end of the fraction instead of
Oh, yeah. You have to be careful with your squares inside the calculator and making sure it squares the right things. Okay. All right, so we've got 48.96 degrees. Let's see where I am here. Oh, okay. Yes, yes. All right, so the next thing we're going to do is we're going to figure out how we do addition inside of, or arithmetic, addition, subtraction, inside of the clock. Okay? This is really a lot like how you do addition and subtraction with just your whole numbers. So let's take a look. This is 89 degrees, 37 minutes, 24 seconds, minus 48 degrees, 57 minutes, 21 seconds. And I realize it sort of looks funny with the spacing and how the Word, probably, how Word did that. So just realize that you can put your little hash marks closer together. They don't have to be spread out funny like that, okay? What we're going to do is we're going to line these up sort of vertically. And we're going to keep the degrees, minutes, seconds.
Wait, is it 39 or 89?
Thank you. 89. I was already ready to do my 37 apparently. Whoops. And then 24. And we're going to subtract 48 degrees, 57 minutes, 21 seconds. Okay, I think I got my notation all in there correct. Does that look okay, you guys?
Yeah.
Okay. The standard way of subtracting, where would we start? On the right-hand side. We have 24 minutes or seconds, and we take away 21 seconds. What does that leave me with? 3 seconds. So far, so good. Pretty straightforward. We run into a problem when we look at the minutes. What problem do we run into?
We have to borrow from our degrees.
Yeah. The problem we actually run into is there's simply not enough degrees to do the subtraction. I'm sorry, not enough minutes to do the subtraction, right? So we have to borrow. Okay? So I'm going to borrow. This 89 minutes is going to become 88 minutes, right? But if I borrow 1 degree, how many minutes is that 1 degree? 60. So I already had 37, and now I have 60. So how many do I have now? 97. So now I have 97 minutes. I'm going to slide this down so that it's not writing on top of my words. Yeah, so then when I do the subtraction, I have 40 minutes, because now I have enough to actually subtract. Then we have the 88 degrees minus 48 degrees, which will give me 40 degrees. So I have 40 degrees, 40 minutes, 3 seconds. Does that make sense? We did this, some of you with me, in number theory when we did addition and subtraction in other bases. This is just specifically done with base 60. That's what we're doing, okay? Well done. As long as you have answers for your minutes, degrees, your minutes and your seconds that are between 0 and 60, you've got the answer in the right form. It's not going to happen on subtraction, but when we get to addition, let's say for something when you did the addition, you ended up getting an answer that had, like 92 seconds? Well, you wouldn't leave it as 92 seconds, right? You'd move it over and you'd actually do the reverse of borrowing, which is what we usually call carrying. And you would actually do it that way. And we'll encounter one of those in a minute, but that's what this note is referring to. All right. So you guys get to practice now. So we're going to take a little time out. We actually have 3 of them, I believe. Yeah, 1, 2, 3 on 2 separate slides. So these 2 and then this one. So the first one, you're going to turn it into the degrees, minutes, seconds. The second one, you're going to turn it, I was about to say turn it out of. That doesn't sound very good. You're going to turn it into just flat out degrees. And then on the third one, you're going to notice that these are the same numbers we had before, but it's addition, right? You're going to add the degrees, minutes, seconds form. Okay? So go ahead and take about, 2 minutes or so. Try these problems on your own. Once you are at the point where you have an answer, check with a neighbor. If you're stuck and you can't get to the point where you have an answer, check with a neighbor sooner, and that's fine too. Okay? Okay, so let's check and make sure we all have the same answers. I think most of you are confirmed with somebody nearby. What did you get for the first one?
56 degrees.
Oops, sorry.
3 minutes.
56 degrees. What was next?
43 minutes.
43 minutes and how many seconds? 12 seconds. And you should have done that basically by taking the 0.72 and multiplying it by 60. And then you ended up getting a decimal portion of that, right? You had the 43 and then a decimal portion of that. Was that a decimal portion? 0.2, and then taking that 0.2 and multiplying it by 60 again to get 12, right?
Yes.
Fabulous. Okay, 2 is a little weird. What did you get on 2?
78.656.
Okay, 78.65, and then it's 6 repeating, which we're okay with writing the repeating bar, okay? And then that's degrees. Okay, is that all right? So that's okay. They aren't always going to work out to being a terminating decimal. That's okay. Repeating decimals are all right. All right, the last one had the process that when we, let's actually just make sure everybody's work looks the same on this one. 89 degrees, 37 minutes, 24 seconds. There's a couple of ways your work could look. I will write it one way, and then I'll kind of make mention of another option. So when we add the seconds together, this is an addition problem. 24 and 21 seconds is okay. That one gives me what? 45 seconds. That's still less than 60 seconds, right? So that one's fine. But what happens when I add the 37 minutes and the 57 minutes? 94 minutes. And for the moment, I'm going to write mine down here like this. This is the sort of optional thing. You don't have to do what I'm doing with the 94 here. I'll show you another step, but I'm just going to break it into 2 steps. What happens when you add the 89 degrees and the 48 degrees? Fantastic. Okay. So this is not okay as your final answer. It's definitely fine in the interim, but it's not okay as your final answer because 94 is bigger than 60. Okay? So what are we going to have to do?
Subtract 60.
Right, so we need to subtract 60 of the 94, which would give me what? 34. And what am I going to do with that 60 that I sort of took away?
Give it a minute.
Yeah, 60 degrees is, 60 minutes is actually 1 degree. So I'm just going to add one more to my degrees. So I'm going to have 138 degrees. You could do that in the middle of doing your addition, if you'd like, instead of doing it as a separate step at the end. So this is what we end up with. Is that good? All right. Definitions. There are 4 types of angles. Do you remember any of them of what they're called? Acute. That's my first one, right? So this one's called acute. Acute means what? It doesn't mean it's cute. It means it's smaller than 90, specifically smaller than. And actually, let me write it a little bit differently. It's actually your angle. Let's give this the label alpha. Your angle is between 0 and 90. We'll write it like that. Let's go to the one underneath it next. What kind of an angle is the one underneath that? That is a right angle. What can you tell me about a right angle?
It's exactly 90.
Yeah, so we'll call this one alpha as well. We'll call them all alpha. So the alpha equals 90 degrees. We'll go back up to the top right-hand corner. This is one sometimes people don't remember. Do you remember what this one's called? Not obtuse. It's called straight. This one's called a straight. You don't see it used very much, but it is called a straight angle. What do you think you can tell me, even if you didn't remember what it was called, about its angle measure? Yeah, it equals 180. Otherwise known as a line, just in case you were curious, it becomes just a line, right? That angle is actually a line. And again, we'll call it alpha. So alpha equals 180 is technically a straight angle. And then down here, this one is the one that you guys wanted to call it, which was obtuse. Sometimes people will have it in their mind obtuse means more than 90, and in some sense that's true, but it's also less than 180. Otherwise, we've got something that's larger. There is another actual piece of language, your book doesn't use it, that talks about angles that are between 180 and 360. We're not going to talk about it, but there is another angle measurement for that. So we have between 90 and 180. And you'll notice all of these strictly say less than, right? Except for the right angle and this, the obtuse and then acute specifically say less than, because then otherwise you're in the other two cases. All right, circles. Moving a little bit into circles. A circle is defined to be the set of all points in a plane that are the same distance, that distance is called the radius, from a single point. And that single point is the center of the circle. So if you imagine, here's my center of my circle, O. The reason this is called a circle is because all of these points along here are the same distance away from this point in the middle. That is exactly what it means to be a circle. When my husband and I talk about the fact that we would like for him to worship in the ministry full time, Shawnee's our center, and we're able to go a certain distance all the way around Shawnee and feel comfortable with our ability to maintain that. And that's a radius, right? That's what we do. We put the center point as wherever, and we say, I'm willing to drive this far. I'm willing to live this far away. That's what we're doing. We're creating a circle. An arc of the circle is any portion or part of the circle that can be drawn without lifting your pencil finger. So when you're looking at this right up here, there's lots of arcs, right? So one of the arcs would be this right here from C to A or A to C. We could go from A to B. We could have a tiny little arc that goes from B to C. We could have a really long arc that goes all the way around the other direction too. Like we could go from B all the way around like this to C. That also would be an arc. Very large arc, but it would be an arc. Okay? It's a good question, and I don't remember. When we encounter it, I'll let you know, because your book will have a way that they will distinguish it, but I don't remember what their book is using. Yeah. Each pair of points on the circle determines two arcs. This is what this is talking about. It determines the shorter of the two arcs, called a minor arc, and then the larger of the three arcs, it's called a major arc. That's what they're going to do. They're going to put a third letter on there. That's a good idea. Yeah. So if they're going to talk about the major arc, the minor arc from C to B, like I mentioned before, they'll just do BC. If they're going to talk about the major arc, they're going to write it including, say, point A. So they'll say something like BAC or CAB. The notation usually looks something like this. So let's use the BA and C since I was already mentioning them. So if we do BC, if you did a line between them, you'd put that line on the top with the arrows, or a line segment without the arrows, or the ray, right? Well, what we do for arc is we put an arc on the top of it. Sounds pretty good, right? And if we do it for the longer one or the major arc, then we will do it for, we'll say BAC. You could do CAB, and you'll go like this. If the major and minor arcs are the same size, that would mean that you've created semicircles. Make sense? Yeah, that's exactly what would happen. So if we were looking at this particular one, there are two arcs that create semicircles. What would those arcs be? Yeah, they'd be DA, right? DA like this or DA like this. You can use a third point if you'd like, but it's the arc DA. They're exactly the same size. They would not be considered a major or minor arc because they're equal to one another.
Is there a different way to write them, or do you still write them?
Because they're a semicircle, it doesn't matter. I mean, you could write it as like DCA or DBA. You could just write it as DA because they're exactly the same amount.
Mark it as an arc, right?
Mm-hmm. Yes. So like this. Yeah, you would. All right. We have one more slide in this section. Yep. Vocabulary. One more. Chord and diameter. Let's do diameter first. We're just going to go out of order. Diameter is the one that I'm sure you would remember. What is the diameter of a circle without looking?
It goes all the way
Okay, all the way across through the center. Yeah, you got to go through the center. So in our picture back over here, there is a diameter that's on the drawing, right? The diameter is actually DA. And it's the segment, line segment DA, right? So over here in our picture, well, it's not the same picture, but the D and the A are still the diameter, so we can draw it in here. So if I draw this right here, this diameter, one of the diameters would be DA. And it is a segment, so we mark it as such. The diameter is not an arc, it's the segment that connects them, so it's DA like this. There's other diameters in this circle, so somebody give me another diameter in this circle. FC, yes, that's true. And you can write it as FC or CF, right? What's another diameter in this circle? BE. Are there any other diameters in this circle?
Just switching.
You could switch letters. That doesn't create different diameters, actually, right? Are there any other diameters in the circle? Sure, there's infinitely many diameters in the circle. We just don't have points to label and give names for them right now, right? So we could create anywhere we like, and we could create another diameter of the circle. Let me draw one in just for fun. That would be a diameter of my circle, right? I don't have a way to label it. I don't have labels for it the way it's currently drawn, but it's another diameter. There's infinitely many of them. Okay? All right, so let's do the other one then. A chord. A chord is any segment connecting 2 points on the circle. This one doesn't have to go through the center. So are diameters chords? Yes, they are. They're chords that have this extra special property that they go through the center. But there are plenty of chords that are not diameters. Can you give me, we'll go with, there's infinitely many again too, and we could write down a whole bunch, but give me one of them. What do you have? BD would be a chord. I'll draw it in just for fun. We'll draw all the chords in. I'll draw them in blue. So BD. This would be a chord. What's another chord do you see? CE. Ah. Okay, let's do one more just for fun.
AF.
Okay, I heard two of them now. AF, and what did you say, Emma? BF. Okay, so we'll just put 4 in. AF and BF. So AF, look, it's a short one, right? That's okay. BF. And we could also list all those same diameters that we listed on the other part, right? Those would also be chords of my circle.